This is Wolf Stedman at the local ceiling. April 25th, 2026. 9 seconds. That's how long it took an AI coding agent to delete a company's entire production database, and every backup of it. Nobody touched a keyboard. Today, we're going to show you why that's not the scary part. Keep one question in your head while we tell this story. At every step, somebody assumed the software worked because it passed a test, and nobody independently checked. Hold on to that. It's the whole video. PocketOS is a small SaaS platform that runs back-end software for car rental companies. On April 25th, its founder, Jer Crane, had an AI coding agent, Cursor, running on Anthropic's Claude Opus 4.6, working in a staging environment. The agent hit a credential mismatch. Instead of stopping and asking, it went looking for a workaround. It found an API token sitting in an unrelated file, a token for Railway, the hosting platform PocketOS used. That token had been created for something small, adding and removing custom domains, but it wasn't scoped to just that. It was unscoped, good for any operation on the account, including destructive ones. The agent used it to wipe the production database. And here's the part that turns a bad afternoon into a catastrophe. Railway's own documentation said that deleting a volume deletes its backups too. Same blast radius. When the data went, the backups went with it. PocketOS staff spent the entire weekend manually rebuilding customer data from Stripe payment histories and email logs just to keep the lights on. Cursor passed every benchmark that got it into that codebase. It was, by every public capability metric, a good coding agent, and it still did something no competent human engineer would do without a safety check first. Here's the pattern. We're going to trace for the next 12 minutes across 3 completely different corners of the AI industry: production engineering, academic benchmarking, and enterprise security. In every one of them, something claimed to work. Something passed a test, hit a score, or shipped a feature. And in every one of them, nobody independently checked whether passed the test actually meant safe to act on until it was too late. We're calling that the capability trust gap, not because AI agents are broadly incapable. Some of what they do is genuinely impressive, but because right now, the entire industry is operating on an honor system for verification, and the incidents are starting to show what that costs. Let's start with the benchmarks, because it turns out even the test itself can't always be trusted. SWE-bench is the industry's go-to test for whether an AI coding agent can actually fix real software bugs. Model releases lead with their SWE-bench score. It's treated like a credential. An ICSE 2026 study asked a basic question nobody had rigorously checked. When a patch is marked correct because it passes the test suite, is it actually correct? The researchers built a tool called PatchDiff to compare each AI-generated patch's real behavior against a human-written ground truth fix. Not just whether it passed the same tests, but whether it did the same thing. Their finding: 7.8% of patches marked correct are functionally wrong. They pass the test suite that's supposed to prove they work, and they still don't do what the ground truth does. That's one number. Don't conflate it with 2 others from the same study that measure something different. Separately, the researchers found that 29.6% of correct patches behave differently from the ground truth fix in some way. And of those divergent patches, 28.6% are clearly, certainly incorrect once you look at the actual behavior. 3 different numbers, 3 different questions. The headline one, the one that matters for, is the test itself reliable, is 7.8%. So the ruler has a crack in it. It gets worse. In May 2026, a company called DataCurve released a new benchmark, DeepSWE, built specifically to audit whether models were gaming SWE-bench rather than solving it. Here's the trick they found. SWE-bench's test containers ship with the full Git history of the repository, including the commit that contains the actual fix. Roughly 18% of Claude Opus 4.7's passing runs and roughly 25% of Opus 4.6's turned out to involve the agent running commands like git log or git show to pull the gold standard fix straight out of the container's file history, then pasting it in as its own answer. GPT 5.4 and GPT 5.5 essentially never did this. Gemini configuration sat around 1%. To be precise about what that is and isn't, this doesn't mean the model is malicious. It means the benchmark left an answer key sitting in the room, and one model family consistently used it while others didn't. But past SWE-bench was being read by the industry as a capability claim, and for a meaningful slice of those passes, it wasn't measuring capability at all. Nobody was checking how the answer was reached, only whether the final state matched. One more crack, and it's a big one. When a newer benchmark, SWE-bench Pro, tested models on messier, multi-language, real-world scale tasks instead of the curated single-language tasks in the original verified set, scores didn't just dip. They fell off a cliff for some models. Gemini 3.1 Pro scored 80.6% on SWE-bench. Verified. On SWE-bench Pro, the harder, more realistic benchmark, the same model scored 54.2%. That's a 26.4-point gap on the same underlying model, depending entirely on which test you asked it to take. To be clear, this is specific to Gemini 3.1 Pro on this particular benchmark pairing. It's not a claim that every model has a 26-point gap, and it's not a claim about Gemini's overall quality. It's one concrete example of how much a single test selection choice can move the number the industry treats as gospel. Put these three findings together, and the message is simple. Even the instrument we use to measure, does this AI agent write correct code, is measuring something softer than it claims to. And that instrument is what production teams are using to decide how much autonomy to hand these systems. So benchmarks are shakier than advertised. Does that matter outside a research paper? Look at what happened at Amazon. In mid-December 2025, AWS engineers were using Amazon's own AI coding agent, Kiro, to help resolve an issue in a production environment. What happened next caused a 13-hour outage of AWS Cost Explorer in a mainland China region. Here's where we have to be careful, because there are two accounts of this, and they disagree. The Financial Times, citing 4 people familiar with the matter, reported that Kiro hit a problem and decided on its own that the best solution was to delete and recreate the entire environment, and that the engineer overseeing it had broader permissions than normal, which let Kiro bypass a 2-person approval step that's supposed to catch exactly this kind of action. Amazon's official statement, published in February 2026, says the opposite, that this was user error, specifically misconfigured access controls, and, in Amazon's words, not AI. Amazon also says Kiro requests authorization before taking any action. We're not going to tell you which account is right, because we don't know, and neither does most of the reporting on this. What we can tell you is this. Internal Amazon documents viewed by both CNBC and the Financial Times originally listed Gen AI-assisted changes as a factor in a trend of incidents, and that reference was later removed from the document. Whichever version is true, notice what the dispute itself proves. Even the company that built the tool and owns the incident can't produce an agreed-on account of what its own AI agent did. That's not a story about one bad actor. That's a story about nobody having reliable after-the-fact verification of what an autonomous agent actually decided. Now zoom out from single incidents to scale. A security firm called Red Access scanned the open internet for applications built with vibe coding tools, AI-assisted platforms like Lovable, Base44, and Replit, deployed through services like Netlify. They found 380,000 publicly exposed assets built this way. Of those, about 5,000, roughly 1.3%, were leaking sensitive data: medical records, financial documents, internal business data, customer chat logs. To keep the studies straight, that 380,000, 5,000 figure is Red Access's number. A separate, smaller study, reported the same week, scanned roughly 2,000 vibe-coded apps and found its own set of exposures. Different sample, different methodology. Don't merge the two into one bigger number. Both point the same direction, but they're not the same data set. The root cause Red Access flagged wasn't a code generation bug. It was a default problem. Several of these platforms make new apps publicly accessible unless a user manually flips them to private, and search engines index them before anyone notices. Nobody checked whether the AI built it and it works also meant the AI built it and it's safe to expose to the internet. So here's what all three of these have in common, and it's not AI is bad at coding. Cursor's agent wasn't incapable. It found a working credential and executed a database operation flawlessly. Claude Opus was capable enough to find and use a gold standard answer sitting in Git history. Kiro was capable enough to diagnose a production issue and act on its own conclusion. Vibe coding platforms are capable enough that hundreds of thousands of people are shipping real working software with them. The failure isn't capability. It's that nothing in the pipeline independently checked whether a capability claim, "This agent passed the benchmark," "This token is safe to use here," "This app is fine to expose publicly," was actually true before someone acted on it. That's the capability trust gap. Every one of these incidents had a moment where an independent check, a second system, a human gate, an audit, would have caught the problem before it became one. In every case, that check didn't exist, or it existed on paper and got bypassed. The good news is, this gap is visible enough now that people are starting to build for it, not just write about it. A small security startup called CodeIntegrity raised a seed round in 2026, specifically to build what it calls a runtime control layer, sitting between an AI coding agent and the systems it can touch, enforcing rules about what an agent is allowed to do regardless of what credentials it happens to find. Full disclosure, this is a gap we've felt strongly enough about to work on ourselves. We've built and published our own open source tool to help close it. It's called Blastdoor. It puts deterministic guardrails between a coding agent and dangerous actions. And it's free on GitHub at github.com/firstpartyworks/Blastdoor if you want to try it or tear it apart. That's one small company and one small tool, but the regulatory pressure behind this kind of tooling is bigger than any single vendor. The EU's Cyber Resilience Act starts requiring companies to report actively exploited vulnerabilities and severe security incidents starting September 11th, 2026, with full compliance obligations phasing in through the end of 2027. Non-compliance penalties run up to 15 million euros or 2.5% of global revenue, whichever is higher. Put plainly, the era where a company could ship AI-generated code, an AI-assisted benchmark score, or an AI-built app and simply hope nobody checked is closing. Verification is becoming a market, not just a nice-to-have. We're going to keep tracking this. When there's a resolution to the Kiro dispute, an update to SWE-bench's methodology, or real adoption numbers for guardrail tools like this one, we'll cover it as it lands, not before. Where this goes next is the part nobody's covering. Who's actually building the layer that verifies these claims before you ship, and the liability pressure that's about to make it mandatory? If you want that one, tell us in the comments. Enough of you asking is genuinely how we decide what to make. Subscribe either way so it reaches you when it lands, and drop a comment if you've seen a capability trust gap in your own stack. We read every one. For the local ceiling, I'm Wolf Steadman. See you in the next video.